Now we will take a closer look at discontinuities and classify them into one of two types. All discontinuities could be either removable or non-removable. Removable discontinuities can be quote unquote removed using algebra. A more precise way to describe this is that it's possible to define or maybe redefine the function at the discontinuity to make it continuous there. A non-removable discontinuity, on the other hand, cannot be removed using algebra. In other words, it is not possible to redefine the function at that point in order to make it continuous there. Let's take a look at some graphs and see what removable and non-removable discontinuities might look like. In the first graph, we have a function that is absolutely discontinuous at x equals c because we have this vertical asymptote. We want to ask ourselves, is it possible to maybe define or redefine the function value at x equals c and make the function be continuous or be in one piece? And no matter where I define the y value at this point, here or maybe here or down here or way up here, the function is just completely separated and you can't connect it together. So this is an example of a non-removable discontinuity. In the second graph, we have another discontinuity at x equals c because we have a jump in the graph. Here, there is a function value at x equals c. So we want to know if we could choose where this function value would be, where the hole is filled in. Could we possibly make this function be in one piece or get rid of this break somehow? And that's just not possible. Even if we open this up and we put the function value down here instead, it's still going to be in two pieces. So this is again a non-removable discontinuity. However, if we look at the last graph, we see that we have another discontinuity at x equals c, but this time we could actually change the function value, which is this point right here, and move it up to the hole. If we did that, then the graph would be in one piece and the function would be connected. So this is what a removable discontinuity looks like. And I realized I just switched the colors here on the removable and non-removable. That's not confusing at all. So just to be consistent, let's make non-removable here, right? Those are the ones that I was describing here in the pink and then removable in the blue. Let's see how to classify discontinuities algebraically into removable and non-removable. When you're finding discontinuities with a rational function, like the one here, remember that all we need to do is find where the denominator can be 0. The best way to do this is to factor the denominator entirely. This is a difference of two squares, so it will factor into x plus 1 times x minus 1. In the numerator, we can't factor that any further, so we have x minus 1. Then, looking at the denominator, we see that we have two discontinuities. We have one at x equals negative 1, and we also have one at x equals positive 1. When we are classifying the discontinuities, we just want to look at which ones could maybe cancel out, which ones would be 0 over 0, which would be a hole in the graph, or which ones would be not 0 over 0, which would be a vertical asymptote. We can see here that the x minus 1s could be quote unquote removed. That is an algebraic way of showing that this x equals 1 discontinuity is removable. Because again, this means that we have a hole in the graph. On the other hand, this x plus 1 gives us the discontinuity of x equals negative 1. We can't get rid of that. This is not a hole in the graph at x equals negative 1. It's a vertical asymptote. And remember that we cannot redefine or define the value there in order to make it continuous. And so this is a non-removable discontinuity. In example 2, we have f of x equals x to the third minus 9x divided by x to the fourth minus x cubed minus 12x squared. We would like to do the same thing here. Let's completely factor the numerator and the denominator. Please pause this video and make sure that you're comfortable factoring something like this. In the top, we have a greatest common factor of an x that we could take out. We'll have x times x squared minus 9. In the bottom, we also have a GCF of x squared, though, that we could take out. This will give us x squared minus x minus 12. I think we can factor each of these parts here further. X squared minus 9, that's a difference of 2 squares. That'll factor into x plus 3 times x minus 3. Then down in the bottom, we've got x squared. This next part is a quadratic with a 1 in front of the x squared. So if it's going to factor, it'll factor into two parts like this. And we're looking for two numbers that multiply to negative 12 and add up to negative 1. Those numbers will be minus 4 and plus 3. Now looking at the denominator, we see that we have some discontinuities. We have 1 at x equals negative 3. We have 1 at x equals positive 4. And we have another one at x equals 0. To determine the types of these discontinuities, here we will look at the numerator. This x plus 3 is a factor in common with this x plus 3 up top. Now we don't want to actually cancel these out, but the idea is that we could, which means that we have a hole in the graph. So this one is removable. Again, because we could cancel these, but we don't actually want to. This is still a discontinuity. We have to include it and not get rid of it by canceling. The x equals 4, there is no factor in common. There's no x minus 4 up top. So that x equals 4 discontinuity is non-removable. The third discontinuity at x equals 0 comes from x squared here. Now, if we cancel out, or not actually cancel out, but think about canceling out this x up top with, well, we can only cancel it with one of the ones in the bottom. We ultimately can't quite remove it all the way. There's still going to be another x down here. So we can't fully remove that discontinuity. So that means that this is actually a vertical asymptote or a non-removable discontinuity. In examples 3 and 4, we have two piecewise functions. The first one is x squared minus 4 for x less than or equal to 0. And the second one is 3x plus 1 for x greater than 0. Let's graph this to determine the discontinuities. I see that the function splits up at 0, so I'm going to probably need both of my positive and negative parts of the x-axis, and I'm not sure about the y, so I'll just kind of center it like this. X squared minus 4 is the parent quadratic or parent parabola, which is the one at the vertex at the origin, opening upward, but minus 4 shifts it down 4 units. You can also just plug in some values to graph this. So when we plug in a 0, we would get negative 4. When we plug in a negative 1, we will get positive 1 minus 4, which is negative 3. And when we plug in just one more, negative 2, we will get 0. We know the shape of this, so we can connect it together. Note that we have a solid filled in point here when x equals 0 because of this equal to here in the function description. Now note that this part is continuous on its own. The x squared minus 4 is a polynomial. The 3x plus 1 is also continuous on its own. So the big question is, does 3x plus 1 meet the other part of the graph at this point down here, or is it elsewhere? Well, if we plug in 0 for x into this part of the function, we will get positive 1. This will be an open circle at that point because we are not actually plugging 0 in, but when we do plug a 0 in here, we're kind of seeing where the hole is. We can already tell that it'll be discontinuous, but just to get a nice picture of the graph, we can plug in a couple more points. If we plug in a 1, we'll get 4. If we plug in a 2, that is 7, and I don't need to know about that for the question here. So we'll just graph it like this. So here we see that we have a discontinuity at x equals 0. We want to classify this into removable or non-removable. Well, it's not like we could factor and cancel anything out, so that's not the way to determine that in this case. We want to see, is there a way to redefine the value at x equals 0 in order to put these two pieces together? And of course there's not. So in this kind of situation, it will always be non-removable. In example 4, we have a similar looking piecewise function. This function is x squared minus 4 when x is less than 0. It's 2 when x equals 0, and then 3x minus 4 when x is greater than 0. Let's make a graph of this and see if we can determine any discontinuities. Well, we already know what the graph of x squared minus 4 is going to look like because we just found it. But this time we're going to have an open circle at the point when x is 0. The other point here was negative 1 comma 3 and negative 2 comma 0. So here is the first part of our graph. The middle part here, when x equals 0, we have a function value of 2. The way that that will look will just, at 0, the point will just be up here at 2. Then the other part of this function here is 3x minus 4 when x is greater than 0. So that's for all x in this direction. This is a line with y-intercept negative 4, and that means that we're going to actually meet this point right here. When we plug a 1 in, we can get another point. 3 minus 4 is negative 1. And then when we plug a 2 in, we will get positive 2. And we know this will be a line, so we can just connect these together. That line is kind of bent. Make believe that it's better. So in this case, again, we have a discontinuity at x equals 0 because the graph is in more than one piece. However, we could actually make it continuous. If only this value here weren't 2, we could define it to be negative 4 if we just redefined this value here. So that's what it means for something to be removable or non-removable. So because we could make this function continuous by just bringing this point down here, then that makes this discontinuity removable now.